Okay, everybody, so here's our video about sound and resonance, kind of discussing what are the properties of sound and what are we looking at. So we think about like different types of sound. We got pianos, headphones, parrots talking, jackhammers, all sorts of different sources of sound. And what really causes that sound to exist? Well, what it is, it's vibrations. And you look here when he plucks the guitar string, you can see that the string itself is vibrating back and forth, generating a wave. So it's playing, messing with the air around it, causing vibrations in the air. Or I think about a bell, right? You hit a bell, it's going to cause the metal to vibrate. That vibrations are going to work on the air around it, generating a sound. Or you might get a slide whistle, where again, we're vibrating air inside the whistle itself, and that's causing different sounds to be emitted based on the length of the whistle. So all of these are all about vibrations in air, and that our ears are going to detect and turn into a sound. So here's kind of a slow motion of a speaker. You can see here as it's vibrating back and forth. What it's doing when it pushes out, it's compressing air. When it pulls back, it's relaxing the air. And the difference between those compressions and relaxations are what's going to generate the sound wave. So you see a little bit here too, where you've got the red thing being the speaker, and it's compressing those air molecules together and then pulling back. And it's working at the same wavelength or the same frequency right now. So you can see that it's generating a single tone, no complicated tones here at all. But you can see the particles look like they might be moving to the left and to the right. But if you look at the little red dots, you'll notice the little red dots just vibrate back and forth. Those would be a single particle in the air around this compression wave. So the particles might appear to be moving left to right. In reality, they're just vibrating back and forth. And it's the density that's changing between them. So here is another kind of example of that. You have our speaker, we have our longitudinal wave, we have our peaks and our troughs, just like we do with our transverse waves. But in a compression or longitudinal wave, they're called compressions and rarefactions. Rarefactions being the places where it's at its least, kind of like the trough, and the peak, max of the compression being kind of similar to the peak of a transverse wave. Again, longitudinal wave means that the energy and particle movement is parallel. So that's why, again, we saw those particles bouncing back and forth on the previous image. So a couple things we can change about sound. We can change the loudness of the sound. That's based on amplitude. So you can see there the speaker, even though it's vibrating at the same frequency, how far it's going back and forth is generating more pressure and therefore generating a larger amplitude wave. So you are seeing a greater loudness. So the greater the amplitude in a sound, the greater the loudness of the sound. That's what's going to affect that. For another property here is pitch. So here we have two sounds that are moving with the same speed, but what they have are different frequencies. And the different frequency of the wave is going to generate a higher pitch of the sound. So you also notice if you have the same speed, that means if you have a higher frequency, you're going to have a shorter wavelength, since velocity is, since v is the lambda times f. If the wavelength goes up, the frequency is going to have to go down. So we have an inverse relationship between the two. So hopefully this graph kind of gives you an idea. The one on the left, this will be your lower pitch sound, and the one on the right will be your higher pitch sound, because it will be at a higher frequency. And both of them will have the same loudness, because you see their amplitude is the same for both. So one other factor into a speed of sound is this equation right here. The velocity of the speed of sound is 331.5 meters per second. And this is in air, plus 0.6 meters per second per degree Celsius times the temperature. So sound is going to speed up in higher temperatures. It's going to slow down in colder temperatures. And think about it, it makes sense. The more the particles can move around, the faster things are going to be able to move through it. And at a higher temperature, the particles are going to be moving more. So now we can also change the speed of sound by changing the medium we're traveling through, like what the sound is traveling through. You can see a couple of those speeds down below. On air, sound's moving at about 340 meters per second at room temperature. Water, it's moving about 1,500 meters per second, and about 5,000 meters per second in steel. So it doesn't mean it's going to transmit very well. It's going to move really fast, but its amplitude might die off because it might not be able to move the particles as much. So you have to be a little careful with that, thinking that, oh man, if I just built something out of steel, I would hear the sound so fast from so far away. But you have to have a lot of amplitude to vibrate this steel because it's got a lot of inertia. It doesn't want to move anywhere. So that's going to determine kind of how quickly a sound wave might move through something. Okay, great. So we got some basic properties. We've got pitch, we've got amplitude, we've got loudness, and we've got how fast sound is moving. Well, here's some things we can do with that. So here we've got force vibrations. They're kind of key for resonance that we're going to deal with soon. A force vibration occurs when an object is forced to vibrate due to some outside force. So maybe like strumming the string of a guitar, hitting a tuning fork with something, some kind of contact. When it does that, that object's going to vibrate at what's called its natural frequency, which depends upon a lot of different factors of the object. Like for a string, its length, what the string is made out of, the tension in the string, lots of different things there. The temperature as well, right? All those things are going to affect the natural frequency of that string, which is why when you play a guitar and you pluck it, if you move your fingers around, okay, you're going to generate different noises. So if my finger was at one spot, it generates one noise. I move it on the same string, I take my finger off, it makes that noise, put it in the middle, and I get a much different noise, a much different frequency. So that's how force vibrations are going to generate the natural frequency of the thing to vibrate. And then when it does that, it's going to force the objects around it to vibrate. Kind of try to get them to vibrate that same frequency as well. This is a thing called resonance, which is the induced vibration of an object by another object vibrating at its natural frequency. This is what we're going to do in our lab. We're going to take a tuning fork and we're going to try to generate that same natural frequency in a column of air. We'll get to that a little bit more later. But some ideas of resonance a bit more here, like in a trombone, right? The lips of the trombone player initiate the force vibration of air in the trombone, and then the sound wave establishes a standing wave in the trombone and the air inside. If we extend the length of the tube by moving the slide, the wavelength of that standing wave is going to change. So that's why with the trombone, you change the pitch by extending the slide forwards and backwards. You're extending the length of the column of air, okay, basically extending the wavelength to change the frequency of the sound that is most naturally vibrating within that trombone. These, you might have played with these before. We'll see these in the demos in the next class. We're going to use these things, boomsticks here. The force vibration hit on the table, but the resonance of the air inside is the fact that after the tube hits, it's going to start vibrating its natural frequency. So each of those tubes, even though I hit them the exact same on a table, they're going to vibrate at a different frequency and generate a different pitch of sound. So we'll see that more in the demo, but the shorter tube is going to have the highest pitch. It's going to have the shortest wavelength and the highest frequency for the sound inside. Whereas the longest tube will have the longest wavelength of sound that resonates inside and therefore the lowest pitch. Okay. So one example of resonance in a sound, this thing called the RUBEN'S tube. You can kind of see it here. It's a tube with lots of holes drilled on the top at set intervals, and it's hooked up to a speaker on one end and a gas source on the other. As you pump the gas through and then you play a sound wave through it, you'll end up generating standing waves inside. You play a single tone. So you can see here we have nodes and antinodes just like we would in a normal standing wave. And the higher points represent the antinodes for your standing wave. So as you change the frequency, you would change like which harmonic you're at. Unfortunately, I couldn't embed the video there. It's a great example of a RUBEN'S tube, so you should go check it out. But just another illustration of what can happen with different sound frequencies and how that relates to harmonics and resonance. Another example would be here, where resonance is actually very harmful. This was a bridge in Tacoma, Washington, called the Tacoma Narrows Bridge. It was built in 1940, finished in 1940, and then all of a sudden, like later in the very first year it was built, due to the high winds that were rushing through, it actually started to oscillate back and forth, up and down like this, rotating around that central axis. Actually generate what's called a torsional wave. But all these vibrations and these waves fed into each other, generating even larger shifting from the center point. Eventually to the point where the bridge actually collapsed. It ripped itself apart based on the resonant waves that were traveling through it. So definitely go check out the link below to see the full video if you want to see the full effect of that. So for resonance in a tube, here's what's going to happen for our lab. So we have two different types of resonance we can have in a tube. The first one is a open to closed end. So here we have an open end, here we have a closed end. What we're looking at is when the tube opens back up to have the largest possible gap between crest and trough. So if you look here, the sound gets initiated up here, hits this end, bounces back like we saw, but bounces back on the other side. So you'd have a crest, you have a trough, you have your largest possible difference. That's where you get the largest possible sound, greatest possible amplitude. So the first harmonic for a closed tube, the length of the tube is 1/4 the wavelength of the sound wave that comes into it. That's why it's 1/4 of the wave. For the third harmonic, you actually have 3/4 of a wavelength. Okay. The thing is, for the second harmonic doesn't exist because the second harmonic, if you think about it, would actually go closed and closed. You would have a point at both ends, which would mean actually the sound is basically nil. There's no sound at the top, right? And every other harmonic is adding an extra half wavelength starting from 1/4 on, is being the length of the tube. Again, here you can see we have you have basically like 3/4 of a wave, but that means in total the sound actually goes 1.5 waves. Here it might go a 1/4 wave down, but also goes a 1/4 wave back out. So that means we have a half of a wave there, but tube is only 1/4 of that wave. For an open-ended tube, a little bit different. Here, your first harmonic, second harmonic, third harmonic. Here, you actually can generate the full harmonics because there's no reflection. So the first harmonic, so you start maximal, you end up maximal. You only complete half a wave, like you would with the normal first harmonic, but you do generate the loudest possible noise at both points. The second harmonic, you complete an entire wave. You go from crest to crest or trough to trough, and you would generate your maximal possible output. So in a tube that's that length, you'd have 5 different tones that are in there, these 5 harmonics. Certain ones will just be at greater amplitudes than others. But what this whole concept like over here is going to allow us to do is determine if we know the frequency of the sound and we know the length of this tube right here, we will be able to determine what is the speed of sound. So again, velocity is frequency times wavelength. We have 1/4 of the wavelength here. We have our frequency is going to be given by the tuning forks vibrated at a given natural frequency. So that'll be how we're going to determine how fast is sound moving in our tube. So the Doppler effect is what happens as objects move closer to you and then move further away from you. What happens to the sound? So if you think about it, if you've ever heard a race from a car, or the train's coming at you, or a car is driving towards you, as that object gets closer to you, the pitch of that sound is going to get higher and higher, and as that car moves away from you, the pitch of that sound is going to get lower and lower. The idea is, well, how does that happen? Well, that's all the Doppler effects. This is called the Doppler effect. So you have an object moving forward, due to and is compressing the sound waves due to its motion. Thus, these sound waves are going to have a shorter wavelength as it's moving towards somebody. Things have a shorter wavelength, speed still the same of sound. That means that the frequency is going to increase because the wavelength's gotten shorter. That means something coming towards you, it sounds like it's at a higher pitch. And the exact opposite of true is something going away from you. As it's away from you, it's almost extending out those waves, right? It's moving away as it's generating more and more vibrations, which means that the wavelength is going to increase. As the wavelength increases, the frequency goes down. So something going away from you sounds like it's at a lower pitch. So even though the sound itself doesn't change, your perception of it does based on whatever frequency you're hearing. So you think about that if you ever watched a car race on TV or just listening to a car go by you or a train go by you or anything like that. As it moves towards you, it's a much higher pitch. And then as soon as it goes past you, the pitch drastically drops. Because of the fact that you're getting compression or expansion of the wavelength of the sound based on the object moving.